Okay, so welcome to class for Thursday, April 9th. It's my brother's birthday. I got to call him later. Forgot about that. Okay, Thursday, April 9th. Today, the plan is we're going to talk about section 3.1 in the stats book. We're going to play around with the Monopoly example a little bit further, and we're going to break up a little early, hopefully, and then I'm going to meet with the Galaxy group for a little while. Generally speaking, so just so we've got all the time straight, the plan is I'm meeting with the Canopy Waves group at 2 on Tuesdays, the Traveling Salestronaut group at 3 on Tuesdays, and the Galaxy group at 10 or immediately after we're done with class on Thursdays. Is that correct?
Yeah, that's right.
Yep.
Hold on one second. James, you can't do Prodigy today. James, I'm telling you no. All right. Yay for parenting. Okay. So we're all set on the group meetings. I do apologize. I don't know what the deal was, but my internet connection was just not playing nicely with Slack on Tuesday, Tuesday afternoon. It would be fine. Like the speed was just fine, and it would be fine for like 5 minutes, and then it would just drop, and I would lose everything, and the Zoom thing would crash. And so anyway, we will hope for better connections in the future. Anything? The other thing we definitely have to talk about, and let me share my screen on this one, is the college poster session. The college poster session is now virtual. We don't know what that means. The college poster session committee is not answering. So they send out an email. Everybody said, "What does that mean?" And then we haven't heard anything back yet. So I don't think they know what it means. But the plan is that it will be, you can upload a PDF of your poster. You could also upload a video of you presenting your poster, which I would encourage everyone to do. So the deadlines are as follows. On April 20th, that's a Monday, so that is a week from this coming Monday, you have to submit an abstract. So here's what I'd like to do. I would like to say that each group needs to have an abstract put together by class next Thursday. I'll send this out in an email so you have it in written form as well, but that'll be the 16th. Okay. So hopefully you've all written abstracts for some other class at some point, but an abstract is a paragraph that basically goes through the same structure as your poster. And we'll talk about this more as we go, but your poster should have the same structure as anything you do, which is basically just, you should have an introduction, you should have methods, you should have results, and you should have what is often called discussion, because conclusions are often a little too far for this. Abstract has the same thing, but in very brief form, right? So you should have a couple sentences of introduction, a couple sentences on your methods, a couple sentences on your results, which our results are still pretty tentative at this point, and a couple sentences on how those results impact whatever, right? So what you'll need to do, what you should start doing with the other members of your group, I suggest just make a Google Doc and start bouncing ideas around. I am happy if you share the Google Doc with me. I'll read it and I'll make comments and suggestions and things. But we need to sort of have those pretty close to finalized by next Thursday. So one of the things we're going to do next Thursday is we'll go over the abstracts in addition to talking about the stats stuff. Okay, are we clear on that? Any questions? The actual posters aren't, we don't have to upload the posters until Saturday, April 25th at 5 p.m., right? So the posters and the videos, those get uploaded later, right? Basically the end of the week. So the week between the abstract being due and the poster being due, we'll work on posters. What this means for us in terms of class results is we need to start generating figures. So wherever our projects are at this point, and some of them are pretty rough, we need to start saving images. So that'll be a little tricky to do, but we should be able to start getting some things. And we'll talk about that in the meetings next week that I do with each individual group, about what kind of images you could be saving, what sorts of things would be useful. Okay. The other thing we'll need to work on, of course, is ways to describe what you're doing. So the methods, right? And hopefully you guys have a pretty good idea of how to describe the methods, but we'll need to start playing with that. Okay, questions, comments, concerns? I feel like we basically lost a month of time, with the whole disruption here, getting back on our feet and getting everything running, which is disappointing because frankly, I think we could productively use another like 6 months of time in this class, but we have what we have. So we'll do our best. Okay. So just to reiterate, abstracts are the first thing to work on. I would have somebody in your group start a Google Doc, share it with everybody, share it with me, and we'll start working on those. We need them in basically a somewhat finalized form by class next Thursday. That's the 13th. Okay, any other nuts and bolts things we need to go over? All right, I see Sean, you've made it. So Sean, tell us all about distributions.
I thought Josh was going to do that.
Oh, Josh. It's Josh.
Yeah,
it's
I
not
think it
Sean,
was
it's
me.
Josh. Okay. Sean, you're off the hook. Although actually that does bring up the point. So for next time I want to do section 3.2. Hold on. I need to make sure we want to do all of 3.2 because if I remember right, it's long. Yeah, we'll do all of 3.2. So who wants to do 3.2 for class on Tuesday?
I'll go ahead and do it.
All right, Dylan, you're up for Tuesday. Okay, Josh, tell us about distribution functions.
Okay, I'm gonna share my screen. Oh, you disabled screen sharing.
Okay, it should be on now.
Okay, there we go. Okay, can everybody see that?
Yeah.
Okay, so chapter 3.1 is on probability distributions. And so what a probability distribution basically is, if you have like a set of random variables or just like data that you get from the real world, oftentimes they'll follow some sort of distribution. And it's nice to know, there's different kind of distributions. So we're used to like seeing like the normal, like nice curve, but there could also be like exponential distributions, which we'll see, and other stuff. So they walk through an example here, but I'm just going to keep moving. So yeah, the first thing they do is define probability distributions. And so they talk about this like capital F of t function, which is basically the probability that x will be less than this value t, and t can be any value from negative infinity to infinity. And then they define some axioms that just have to be true. I don't really understand why, but they just do, I guess. And
So
then they go into
I'll chime in on why those have to be true. So the idea behind the cumulative distribution function, that capital F, right, is it's the probability of your event being less than some value, right? So the bigger you make that some value, the higher your probability has to be, which is why it can't be decreasing, right? Because each time you up that limit, you've added more possible outcomes to your group, and so the total probability of getting one of those outcomes has to go up each time you make it bigger. And then the reason negative infinity has that value of 0 is that's the probability of having no outcomes, and at infinity it's the probability of all the outcomes of being, which is just 1.
okay. So the next thing they do is talk about discrete distributions versus continuous distributions. And so discrete distributions are where these the events that you have like set values. So if you're talking about like rolling a dice, there's a set number of values that it can take on, 1 through 6. And the thing that you can do with discrete distributions is the probabilities, if you sum them all up, they'll add to 1. So if you're talking about the dice example, the probability of getting any one of them would be 1/6. And then if you add them all up, that'll equal 1. And so finding, I guess, the probability of any one of those would be this capital F function that we saw above. And then it's x of I, and then plus this like small value, and then minus capital F, and then x of I minus that small value. I also didn't really understand why we're doing that, but so, and then it goes through this probability for a dice, right? And if we added all those up, it would equal 1. Yeah, and then for continuous distributions, it's a little different. So continuous distributions can take on like any value within a range. So in discrete distributions, it can only be like 1, 2, 3, 4, 5, or 6. But like continuous distributions could be like 1.1 or 1.001 or 1.00 pi or whatever. And so when we talk about discrete distributions, we say that there's the n is either finite or like countably infinite, but for continuous distributions, it's like uncountably infinite. And so if we scroll down, we can see like, I don't know, I guess some consequences of that. And so the first thing they do is talk about this f of x, which is the probability distribution, and that's the derivative of capital F of x. And so let's see. If you talk about, when you talk about the probability of continuous distributions, you talk about them within a range. So you can ask like, what's the probability that x is between x1 value and x2 value? And so what that comes out to is the integral from x1 to x2 of this probability distribution function, which is like kind of a lot to take in. But one thing that's like important to notice is that for discrete distributions, each value in the, it's called a support, but like whatever values it can take on, um, those all have probabilities themselves. So 1 has a probability of 1/6, 2 has a probability of 1/6. Um, but for continuous distributions, we can't do that anymore. So we can't assign a probability to any one value. I mean, we can, but the probability that it's any one value is 0, because that would mean that x1 is equal to x2. And then if you took the integral of that, it would just be 0. Um, so the probability that it's any one value for a continuous distribution is 0. So you have to talk about a range. And another way to like visualize that is like with, if you plot f of x, you can see they're talking about a range here, and there's some area, right? So that's the probability is this area. So if you were to just talk about one point, you can see that there wouldn't be any area because it'd be like, it wouldn't have any width. And so, yeah. So this example is coming from um, uh, an example of like an exponential distribution, which I was talking about before. And it's the decay time of an unstable particle, whatever that means.
I'm going to
So,
assume that's a typo and it should be unstable, but an unstable
oh,
particle could be fun.
okay. But I guess that's not super important. The important thing is that it follows this distribution. So f of t is the probability or the density function. And so since it's exponential, it follows this rule. F of t is t given lambda is equal to lambda e to the negative lambda t. And so they also find capital F of t by taking the derivative, or sorry, the integral. Um, and then we can also talk about p of t is greater than tau. And we get that from this integral. And so then we can answer like interesting questions, like what is, um, so t is, or tau is like, I think the half-life or something. Let's see. Well, whatever it is, you're basically asking like, what's the probability that a particle lasts longer than whatever this value is, which might be good to know. So, and then they go into another example. And so it's an oxygen atom is drifting in argon gas driven by thermal scattering. And then it looks at its position in the X, Y, and Z coordinates. And so this probability density is going to follow a normal distribution. And we just kind of know that, like same for knowing that this is like exponential distribution. We just kind of, I don't know, that's kind of just given to you. So I'm not sure. But yeah, so if you look at, that's not what we want. If you look at the normal distribution, you can see that f of x, the probability distribution or the density function, is equal to this ugly thing. But basically what it comes out to is like you get this really nice curve, which probably most of us are used to. It's like a Gaussian curve or whatever. So this is your like f of x, so your density function. So if you were to plot, I guess if you're plotting, you know, where everything falls on this scale, most of them are going to fall here, and then some of them are going to fall here, and then very few of them are going to fall over here. And then the very last thing they talk about is empirical distributions, which is kind of what we did with the monopoly example. So basically, like it might not always follow this normal distribution, or like it might be, the process might be like too complex, or like we don't understand it very well, so we don't know if it's normal or exponential or whatever. Um, so it might be more useful to approximate it. Um, and the best way to do that would be like to take a sample like we did and look at observations, like for what we did with Monopoly. Um, and the quality of our approximation depends on the available number of observations. And we saw that when we did like a larger sample size, and we saw that the data started to like converge and look prettier. Whereas when we had a small sample size, it was like there were ugly boxes and stuff. And so, yeah, I think that's everything.
All right, questions? Okay, well, good job. We'll clap. Yay for clapping. Okay, so the key point in this section is this concept of the probability distribution function and what is often called the cumulative distribution function. They also called it the integral distribution function. I've never actually seen that used anywhere else, but doesn't mean it's not. And so what I thought we'd actually spend just a minute doing is looking at these for the monopoly example. So let me share my screen. All right, is this big enough for you guys to see?
Yeah.
Okay. So this is the same thing we were doing before, right? We're gonna do 100,000 rolls, or 100,000 turns. I should be careful there. 100,000 turns of Monopoly. And all we did here is figure out how to deal with the fact that if you get doubles, you get to roll again. And if you get doubles again, you get to roll one more time. And really in Monopoly, if you get doubles a third time, you go to jail. But we're not going to actually go to jail at this point. So we figured out some things, right? And what we actually ended up doing here at the end, if we look down here, is we ended up creating a histogram of that data, right? So if I roll this thing, you'll see that we actually created a histogram of our data. And we can actually get those values. So it turns out that the matplotlib.hist function returns what I'm going to call our PDF, our probability distribution function, and our bins, which the bins we actually gave it, so we actually don't need them back out, but we could get them. Okay. So if it wants to return more than one thing, and I only want the first thing, you can just do a comma and then leave it blank. If we wanted to get the bins, for example, say we hadn't chosen them for it, we'd have to grab the bins as well. But for this, so if I run this thing, oh, what did you not like there? Oh, maybe it's returning as a tuple. Okay, let's do this. We'll just put it in temp and we'll see what comes out. Okay, so temp now, yep, is a tuple. Okay, so it doesn't do separate arguments, but it has a tuple of the first thing is our values, right? The values of the probability distribution function, of our histogram, right? Which is a probability distribution function as long as we have a big enough, or is an approximation of our probability distribution function. And then the bins, right? So we really only want the zeroth thing. So we're going to say our PDF is equal to temp sub 0. Okay. And voila, if we do that, we should find over here, we've got this lovely thing called PDF that contains the probability of getting any one of these things that go along with the bins, right? And there we go. Okay, so now what we have is we have a discrete distribution of probabilities. If we wanted to, instead of looking at the probability of each roll, we wanted to ask questions like, what are the odds of moving less than 5 spaces? We could do that by looking at the cumulative distribution function. So the CDF is just the sum up to a given value of our PDF. So it turns out that we can get that in NumPy using something called CumSum, which is cumulative sum of our PDF. And we're going to also give it, let's see what that kicks out, because I believe that's going to be one value short. Okay, so our CDF only has 30, oh no, our CDF has 34 values. Cool. So it did it right. And you'll notice if we plot this thing, right, if I come down here and I say plt.figure CDF, and I plot our roll bins and our CDF, and I want to plot them as points. Let's make them red points. And our labels here are still going to be the number rolled and the chance of, or the number moved, really. Let's be more careful. Number of spaces moved and the chance of moving at least that far. And we run this thing. Oh, it doesn't like that. Why doesn't it like that? Oh, I know why. Okay. Okay, so it's a fun little fact. If you give it the bins, it turns out what you're doing is you're giving it the edges of the bins. And then what it returns, I believe, is the centers of the bins. We'll find out. But basically it means there's one fewer center than there are edges. So let's see if that works. Nope, still doesn't like that. Nope, that's not what I wanted to do at all. Okay, what's in his bins? Oh, it's still returning the edges. Okay, fine, we'll do it your way. So I don't need this because it returns the same thing I put in. But what I'm going to do here is I'm going to do roll bins up to, but so not including the last one. See? Okay, so now we have two different plots here, right? So this is our probability distribution function. It's discrete, right? It has discrete values, but we can do all the same mechanics on it if we just think of those discrete values as just making this a continuous function out of delta functions, right? We just add up a whole bunch of delta functions, we weight them all by the right amount, and we can think of it as a continuous distribution, okay? And you can see that we've got this cumulative distribution. So, for example, you'll notice that there is a 87% chance that you're going to move less than 11 spots, up to 11 spots, right? Because this lovely figure, which I can make a little bigger, right, it pretty steeply increases up till 11, and then it flattens out. Because to get past 11, you not only have to get doubles, but you have to get the right kind of doubles, right? Because if you get doubles like ones or twos, well, that doesn't get you past 11 necessarily. And then you see you have one thing going here, and then you have another slope going there, and then right about here, you flatten out again, okay? So what's the point of looking at this? Well, we know where this data came from, right? Because we built it. So we know exactly how we got it there. But if you were looking at this and you didn't know exactly what happened, you could look at this and say something about it right away. You could say that there are 3 different processes at play here. Because I have one very distinct behavior here. I have another, let me turn on my thing so you can see my cursor. I have one very distinct behavior there up to 11. I have another distinct behavior out here maybe until like 21 or 22. And then I have another distinct behavior out here out until 36. So what this tells me and why we look at these things is because different physical processes will produce different types of shapes in these distributions. And so by looking at them, we can say something about the type of distribution this is, right? We can tell something about the physical processes that went in to make this distribution, which is kind of cool, right? It's really kind of neat that just by looking at this sort of abstract statistical thing we just decided to plot up, we can tell you something about the underlying way it was generated, right? Which if this is data or if this comes from a simulation that solves physics equations, tells you about the physics, which is really neat, okay? Questions, comments, concerns, thoughts?
So for the y-axis,
Yep.
like if you're on 10, it's the probability that you'll get something less than or equal to a 10?
Yes.
Okay.
So it's the cumulative probability, right? So it's the probability that you're going to get a 3, 4, 5, 6, 7, 8, 9, or 10.
Got it. Okay.
And it is really kind of interesting. You might, like, I wouldn't necessarily expect this to tell us anything profound, right? Because it seems like kind of a weird thing to plot up, to just choose to plot the probability of getting something less than some number, right? But it turns out that it works. It turns out that it actually does tell you something about the underlying way that the data was generated. Because it turns out that generally different physical processes will have different behaviors in these cumulative distribution functions. We can actually kind of see that in the probability distribution function as well, right? You have sort of one behavior here, you have another behavior here, and you can't see it very well, but there's another behavior over there. Oftentimes to fix that, people will make the y-axis logarithmic here. Okay, and you can see it a little better, right? You have something going on here, something going on here where it's flat, and then you have this very steep fall off, right? Almost exponential fall off as you get in the probability as you get out to, like, you know, rolling a 35 or a 36. Okay, how we feeling? Okay, so that's today. That's what we wanted to go over today. Next time we'll talk about moments of these distributions, which are things you already know something about because the most common one is the mean. right? But okay, and sorry, Dylan is doing that on Tuesday, correct?
Yeah.
Okay. Well, I'll just announce it's Sean anyway, just to keep his life interesting. But it's actually Dylan. All right. So we'll stop there for today. I will. Well, I don't know. Do you guys want me to update this code on the Slack channel, or we didn't add very much?
It's up to you. I think it'd be a good thing to have on the Slack channel, just so we
Okay.
can like, see.
I'll keep updating it then. Okay. Well, great then. I'm going to stop the recording and we'll be done for today.